So we have an object of mass 3m initially at rest, so momentum is 0. And then we have two fragments when it explodes, one of mass m1 going to the left, let's say m2 going to the right. If we have double the mass, we'll have half the velocity because we're going to maintain the same momentum. So do they fly off at right angles? No, they're not going to fly off at right angles. Do they fly off in the same direction? No, we're going to maintain momentum, and if they flew in the same direction, that would be a positive momentum. We're maintaining 0. The smaller fragment will have twice the speed as the larger fragment. Probably that would maintain the same momentum of 0 once you added them up. Larger fragment will have twice the speed. No, because then it would have twice the momentum. The smaller fragment will have 4 times the speed. No, because then it would have more momentum. So definitely C. 100 kilogram cannon at rest with a 10 kilogram cannonball. So we know it's at rest, so we know the initial momentum is 0. That means they have to be equal to each other but in opposite directions. Or we can just set the momentum after the explosion of the cannon equal to the momentum of the cannonball after the explosion. So we'd have 100 times v, the mass of the cannon times its velocity is equal to 10 mass of cannonball times the velocity of the cannonball, 100 times 90, giving us 9b. Number 3, so we've got an 80 kilogram astronaut carrying a 20 kilogram toolkit, and they're drifting towards a stationary space shuttle at a speed of 2 meters per second. We're going to add up their masses because they are one big mass that are going to then separate like an explosion. 80 plus 20 times 2, their velocity, is equal to, after the explosion, 80 times v, astronaut times their velocity, plus the mass of the toolkit times their velocity, 20 times 6. 20 times 6 is 120. 80 plus 20 times 2 is 200. 200, subtract the 120 to the other side, divide by 80, we get 1 meter per second for that velocity. And it's towards the shuttle because initially they're moving towards the shuttle. And it's positive. We called going towards the shuttle positive. Our final answer was positive. So, number 4, 58.5 kilogram astronauts floating towards the front of her stationary ship at 0.15 meters per second relative to the ship. She wishes to stop moving relative to the ship. She decides to throw away the 2.5 kilogram book she's carrying. What should the speed and direction of the book be to achieve her goal? So she's going towards the ship. It's one big mass. She's going to throw it away from her, and then we're going to see how fast she's going to do that. If you're moving towards the ship at 0.15 and that's positive, that means if we get an answer that's positive, that will also be towards the ship. Combine the masses multiplied by the initial velocity is equal to the mass times velocity plus she's 0, so we don't have to add that in. We're only looking at the velocity of the book. We don't have to incorporate the astronaut on the back end because the astronaut has no momentum. They're coming to rest. Number 5, Jennifer is walking at 1.63 meters per second. If Jennifer weighs 583 newtons, what is the magnitude of her momentum? We know that momentum is mass times velocity, so we need to know what Jennifer's mass is. If she weighs 583 newtons, that is her force of gravity. Divide by 10, 58.3 is her mass. And then we're going to multiply by 1.6 her velocity to get her momentum. So 58.3 times 1.63 will equal, grab a calculator and let's type this in, get this done. $93.28. And the closest answer to that in our list is the 97A, probably set up for 9.8 gravity. Number 6, a 50 kilogram boy running at a speed of 10 meters per second jumps onto a cart as shown in the figure. The cart is initially at rest. So the momentum of the boy is going to be mass 50 times 10, which is his meters per second, his velocity. So his momentum is 500. The momentum of the cart is 0. So we know the initial momentum or the momentum at any point would be 500, and that's equal to 2.5, the velocity they give us, times the mass of the boy plus the mass of the cart, because it's a combined mass. So 500 is equal to 2.5, parentheses 50 plus m. Distribute the 2.5, and then you're going to get 500 is equal to 125 plus 2.5 m. Subtract the 125 to the other side, divide by 2.5. You get 150 for the mass. Going to the back page. On the back page, we're going to set this up. These are collisions. We're going to do this as m1v1 naught plus m2v2 naught is equal to m1v1 final plus m2v2 final, maintaining our momentum. When they give us M1 and V2, M1, M2, they give us V1, V2, and then V1 final, V2 final. We're just going to set up the momentum before is equal to momentum after. So momentum before 120 plus 0 is equal to 12V plus 60, just using the masses and the velocities for each row. When we subtract 60 to the other side, divide by 12, we get 5. For number 8, M115, initial velocity 10, so that's 150, plus M2, V2, which would be 5 times 3 is 15, is equal to 15V, the mass times an unknown velocity, plus 5 times 14, 70. 150 plus 15 minus 70 divided by 15, 6.33. The next one, we have 50 plus 0 is equal to 5V plus 50. Subtract 50 to the other side, you get 0, and then divide by 5, still 0. Number 10, mass 112, velocity 15, so 12 times 5 is 60. The second one has mass 12, but a velocity of negative 5, so negative 60. So we have 0 on the left is equal to 12V plus 60. Subtract 60 to the other side, divide by 12, we get a negative 5. Final one, 30 minus 50 is our initial momentums, is equal to 10V plus 36.665. So 30 minus 50 is negative 20. Subtract the 36.665, then divide by 10. I got a negative 5.67 meters per second.